Welcome to the video on uncertainty in measurement. So, no measurement is exact, right? There's always some uncertainty in the measurement because what we're doing here is we're comparing the object that we want to measure, let's say this blue line, against some known standard, our ruler, our balance that's been calibrated, something like that. So, but we're always guessing exactly where is the beginning here, because we have to match up the left side of the line with the 0 mark on the ruler, and we have to match up the right side of the line with some point on the ruler. And so we're always guessing, where exactly is that? Where is this side? Where is that side? There's always some inexactness, right? We can't ever get our measurement to be perfectly exact. Now note here that counting is not the same thing as measuring. With measuring, we're comparing two objects together. Right? We're comparing some object against a scale. With counting, we're not doing that. We're counting things exactly. If I'm counting pencils, assuming that I'm counting correctly, I know exactly how many pencils I have. Right? So, if I count up 7 pencils, I know I have exactly 7 pencils. I know I don't have 6 pencils or 8 pencils. I know I have exactly 7 pencils. But if I'm going to measure this line, I can't do that. I can't say, well, it's exactly 15 centimeters long. Because it's not 15 centimeters long, but it's not 16 either. It's somewhere between 15 and 16. So in here, we have to estimate where exactly is that line. So there's always some inexactness. Your measurement may be different than my measurement. But counting, if you count those 7 pencils and I count those 7 pencils, we should get the same value. If we don't, one of us has made a mistake because the value is some whole number. Right? So counting, if you're going to end up with some whole number, right? How many people are there in the room? No person is half a person or 0.9 of a person. Right? They're either a person or they're not a person. Right? They're all people. Likewise with the pencils, you don't have 6.99 pencils or 7.01 pencils. You have some whole number. That's a counting thing. Right? So there, it's exact. If you're counting, you have an exact number. So now let's look at accuracy and precision. With accuracy, what we mean is how close the average of a group of measurements is to the true value. Not how close any one measurement is, how close the average of our measurements are. With precision, we mean how close together our group of measurements are to each other. But that has nothing to do with how close they are to the true value. Right? Our group of measurements could be really close together to each other, but really far from whatever the true value is. Or we could have a group of measurements that is really pretty scattered, but the average of those measurements are all right on the true value, whatever it really is. So, I like to use a dartboard, a target. Right? So, we have low accuracy and high accuracy, and we have low precision and high precision. So, if we have low accuracy, remember accuracy means how close we are to our true value. In this case, our true value is symbolized by the bullseye of the dartboard. So if we have low accuracy, that means the average of our groupings is not close to that bullseye. So maybe we have, but also remember we have low precision. So precision means how close together our measurements are grouped. So we have low accuracy, low precision. So we have maybe maybe a point way out there, we've got a point over here, we've got a point up here somewhere, and a point down there. Right? So the average between those 4 measurements, those 4 darts as it were, is somewhere in this region, which is not all that close to the bullseye. And they're also fairly spread out. So let's take our low accuracy, but let's change it into high precision. So we need to get all of our measurements closer together. So let's keep the average. So the average there was around that point. So let's keep the average in the same spot. So we want to keep the average there. But now we want to cluster our measurements closer together. So we'll have one here, and one there, and one here, and then maybe one there. So now all of our measurements are very close together, much closer than they were over here. So these measurements are more precise, but they're still pretty inaccurate. But now let's go back to our low precision case. and move to high accuracy. So again, accuracy means how close we are to our bullseye, our target value. So that means now we need to move our average value there, but leave our values spread out. So if I put one sort of on each sort of corner, the average between those will average out to be that bullseye, roughly. But they're all spread out. Right? If I were playing darts, I would get a terrible score for this, because it's nowhere near the bullseye. So now let's move to high accuracy, so keeping our average on the bullseye. But now let's get high precision, so group our measurements closer together. So now that's maybe something like this. So in this case now, if we're playing darts, we have a very high score. We may not have actually hit the bullseye, but we're pretty close. Right? All of our measurements are clustered close together, and the average of our measurements is in the bullseye. This is the sort of thing that we want when we're measuring things in the lab. Because a case like this is really, really bad. We really have no idea where that average really truly lies, because every measurement that we add is going to move that average around a good bit. In this case, at least we're precise, but we're going to end up fooling ourselves into thinking that, oh yeah, our data is all really close together. That means that the true average really is there. The true value really should be there. But it's not. We're off by some amount. In this case, this is probably the best of those three, because at least in this case, we could just take a very, very large number of measurements, just keep repeating our measurements over and over and over again, and if we average a very large number of samples, we'll find out what the true value is. But that's really time consuming. What we really want is over here. We want to be able to take just a small number of measurements. You know, in this case, 4 measurements is pretty good. We have a pretty good idea what the true value really is. Right? And so this is where we want to be. We want to have high accuracy and high precision whenever we're measuring something. So, there are 2 different types of error that come about. One type is random error, which is a measurement has some equal probability of being too high or too low because of this error. So large random errors are often caused by poor experimental technique. So if I ask my daughter is 3, if I ask her to go and measure the length of a pencil, let's say, she's going to be giving me wildly different values. But she's not going to be always giving me values that are too low or too high. She's just not very careful with how she measures things. On the other hand, a systematic error is a measurement that has an unequal probability of being too high or too low due to this error. So that means that it's more likely to be too high or more likely to be too low. And so systematic errors are generally caused by a flaw either in the measurement technique or in the execution of the measurement technique. So if I have, say, a balance that is not calibrated correctly, let's say it's calibrated, it will always give us low values. Well, every time I put an object on the balance to measure the mass, I'll always be getting a low value. If I have just a very old balance that is in disrepair, that is not giving me reliable numbers, if it's giving me random errors, so I put an object on the balance and it reads 10 grams, and the next time I put it on it reads 20 grams, that same object, without changing anything in between, that will give me random errors. It may also be giving me systematic errors. But if every time I put the mass on the balance, it gives me the same mass, it's just wrong, that's a systematic error. So, suppose you're throwing a party, and you want to know how many people have shown up to your party. You can walk around through each room in your house, and you can count the people in each room. But you're probably going to be making some mistakes. Assuming that you have a fairly sizable number of people at your party, and not just, say, 5. 5 is probably pretty easy to count. But if you have 100 or so people there, you're going to get some errors. right? You may have some random errors that might occur if, say, people are moving around between rooms and somebody moves from a room that you haven't counted yet into a room that you have. Well, now you're not going to have counted that person. On the other hand, if somebody moves from a room that you've already counted, you counted that room with them in there, to a new room that you haven't counted yet, but you're going to come in and count to them again, well, now you're going to have counted that person twice. Now, one would hope that, people would be moving in and out of rooms at roughly the same rate, and so one would hope that if you're really counting this, you'll get pretty close to the true value, and you probably will. Unless somebody's hiding from you. That would be a systematic error. If somebody's hiding from you, they're noticing you coming into the room and they run away into a different room. And if they do this through all the rooms in the house, you're not going to have counted that person. On the other hand, if you make some mistake, if you don't realize that people are out on the front porch, let's say, well, if there are 10 people out on the front porch, you won't have counted any of them. And so that may introduce a systematic error. And we can do the same things in the lab, of course. So how does each type of error, systematic or random, how does each type of error influence accuracy and precision? Does random error increase or decrease accuracy? Does it decrease or increase precision? Does systematic error increase or decrease accuracy or precision? So I'd like you to pause the video and think about these questions and try to come up with what you think the answer is. So, random errors, remember, increase the spread in repeated values. Right? If we take a number of measurements, well, with a random error, sometimes it's going to be too high, sometimes it's going to be too low. This means that we're decreasing the precision, but we're not necessarily changing the accuracy. Right? Because if we have an equal chance of getting a value that's too high as too low, that means over a large number of values, the average averages out to be the true values. That we haven't changed that, unless there's something else going on. But so the random error changes the precision, it decreases the precision, but it doesn't change the average of our large group of values, which means it doesn't change the accuracy. So you may have some random error that could be pretty bad, but if you take a very large number of measurements, you'll get pretty close. Your average will be close to the true value. On the other hand, systematic error shifts the position of values in a particular direction. If our measurements are more likely to be higher than the true value compared to the low, then we're decreasing our accuracy because we're shifting our average of any group of measurements away from the true value. So we're decreasing the accuracy. But we're not changing the variation amongst a large group of values. We may just be shifting the whole group up or down. Right? If you forget to count the number of people on the porch, well, you're just shifting down all of your measurements by the same amount, by the same number of people. So we're not changing the precision with systematic error. With systematic error, we're changing the accuracy, we're decreasing the accuracy. With random errors, we're decreasing the precision. So we want to eliminate the random errors and the systematic errors to have as high of accuracy and as high of precision as we can in our measurements. So that was uncertainty in measurement.